This is Assistant Professor Nimish Das here from LG Institute of Engineering and Technology. In the previous session, we have discussed about the electronic materials. So now onwards, we will start with a new chapter, that is the semiconductors. So in that session, we will first discuss the types and the properties of the semiconductor. So before we start with the properties of the semiconductor, let us clear that thing. The properties that are mentioned out here are the points that is actually available in the semiconductor ideally. Okay. So the presence of the properties that we are expecting would be in the ideal condition. So let's begin. Basically, what are the semiconductors? The solid materials having electrical resistivity between the conductor and insulator are known as a semiconductor. So basically, what are the semiconductor? There is an atom, okay, and its outermost orbits are actually partially filled. Okay, what is partially means whatever the maximum number is just the half of it. For example, the outermost orbit limit is 8, so just half, that is 4 would be available. Okay, that is why it can neither donate, neither it can accept it. So what happens now? All the atoms are there adjacent with the 4 electrons in the outermost orbit. Now what they will do? They will share it. And as they share, what will happen? They all will get 8 electrons in their outermost orbit and it will be balanced. But the sharing of the electrons, that concept is known as nothing but a covalent bond. And covalent bond is one of the strongest bond available. You have seen the same thing in the semiconductors when we were describing in the electronic material that the forbidden gap available was comparatively small, okay, than insulator, but comparatively large than the conductors or metals. Okay, so this is the reason it is between the resistivity, that is the electrical resistivity between the conductor and insulator. Okay, so now let's start the properties of the same. Now the first property, they are metallic in nature. Now what do you mean by metallic in nature? Means the conductivity. The context is regarding the conductivity. So it is having conductivity almost like a metal, okay, but it is not like a insulator. Okay, so it is near to a metal but not as an insulator. After that, they are a bipolar. Now, what do you mean by bipolar? The charge carriers can be your hole as well as it can be electrons. After that, they behave as an insulator at 0 Kelvin. What does that mean? That means that at 0 Kelvin means no external temperature is provided. Okay. So what happens? This covalent bonds cannot be broken down. Now, as they cannot be break down, you don't get any extra electron. Now, no extra electron, there will be no flow. That's why they behave as an insulator. They have a completely filled valence band and completely empty conduction band at 0 Kelvin. Obviously, if there is no flow or no extra electron, how will you get anything in the conduction band? That is why it's saying that at 0 Kelvin, the conduction band is empty. They have a negative temperature coefficient of resistance. Why it is so? Because as the temperature increases, what will happen? The bond will slowly and gradually get break down. Okay. So as the bond breaks down, you will get more amount of electron. So the more the temperature, the more the conductivity, hence the less the resistance will be provided. So this were the properties of the semiconductor. Now we'll discuss the types of the semiconductor. In that, first would be on the basis of the constituents. On the base, second would be on the basis of energy gap, third would be on the basis of impurity. Let us start with on the basis of the constituents. First is the elemental. Now, as the name suggested, elementals are those semiconductors that composed of only single species of atom. Means in entire structure, only single type of the atoms would be available. In short, there is no other element group or other element is present there. The best examples are your silicon and germanium. Okay, so they in all the atoms throughout the structure would be of silicon or it would be of germanium itself. Okay, so now the types of the semiconductor on the basis of the constituents. Now after elemental, obviously the second would be compound. So now the compound semiconductor are those semiconductors who composed of two, okay, and more than two of the species of the atom. So we can have the combinations of them. For example, if we consider 3 to 5 compounds, example is gallium arsenide or gallium phosphide. Okay, so in that what happens? Gallium is there as well as the arsenide atoms are also present. Okay, similarly, if we take the three types, that is the gallium arsenide phosphide. So in that you have got the three of the elements present. So another examples of 2 and 4 are also there. Okay, that for example you can go with the ZNS. Okay, that are the example of the 2 and 6 compounds. Now after that, the second type, that is on the basis of the energy gap. This we have already studied. Okay, so again we will revise it. That is DBG, and DBG stands for direct band gap semiconductors. The semiconductors in which electron falls, recombines with the holes and releases the photon. Okay, we have studied this in EK diagram. What was that? If the both the momentum of conduction band tip as well as the valence band tip are same at the same momentum, what happens, the electrons, that is in the form of electron plus hole. So electron was getting back from the conduction band to the valence band, they were combining, and the energy that was generated was in the form of light, and that is the reason it is known as radiative recombination. Examples are gallium arsenide and gallium arsenide phosphide, and we also say that DBG is nothing but in LED. So that is the only reason in LED we get light. Okay. Now from that we have got now another type, that is IBG. That we know that it is indirect band gap semiconductor. Here the semiconductor in which excited electron falls and recombines with the hole to dissipate heat. How does that happen? Okay, so now the momentum are not same. So in matching of that momentum, that whatever the extra energy is there is dissipated in the form of heat via lattice structure. So what was happening during the recombination? Electron plus hole was generating heat, and they are known as non-radiative recombination. Examples are silicon and germanium. The types of the semiconductors, now the last category on the basis of impurities. So when we are getting on the basis of the impurities, first is intrinsic. In intrinsic semiconductor, the pure semiconductors are called as intrinsic semiconductor. Means it is the purest form of the semiconductor available. Examples are silicon and germanium. Second is an extrinsic type, extrinsic semiconductor. In that we get impurities in that. So impure form of semiconductor obtained by addition of impurities. Okay. So this addition of impurities is nothing but a doping process. Okay. I just give you a one day-to-day example. You see, we don't have the 24 karat gold. Why? Because it will be not remain its own shape because of the 24 karat thing. So what we do? We add some impurity so that it holds its shape. So sometimes for the betterment of the material, we need to add impurity. This is the same reason. Due to covalent bond doesn't break easily, that's why the conductivity was affected in the semiconductor. So by adding the impurity, we are increasing the conductivity of the semiconductor. In that, if that impurity is trivalent impurity, it would be falling in the p type, and if it is a pentavalent impurity, it would be going under the n type. Now the extrinsic semiconductor, so you can see that in that p type, for example, we are taking the atoms of germanium. In that one we are adding a trivalent impurity. Okay, so you can see that, see, trivalent means outermost orbit 3 electrons. Okay, and we need 4. So one deficiency would be there of electron, and that is hole. Okay, and that deficiency is hole and it is positive in nature. That's why it is known as p type semiconductor. You can see that the conduction band and valence band, they are of the germanium. Okay, and a one level is created just below the Fermi level, that is an acceptor energy level. That is because of that trivalent impurity that you have added. So what happens when the trivalent impurity is added? It accepts the electron. That's why that energy level is known as acceptor energy level. Similarly, we have got n-type semiconductor. In that we are adding pentavalent. So pentavalent means we require 4 for bonding. Okay, but one is extra, and that extra is your electron, and it is negative in charge. That's why it is n-type semiconductor. Okay. Similarly, here what will happen? Just above the Fermi level, one another extra level is there. Conduction band and valence band would be of germanium, but that donor energy level. So why it is known as donor? Because that extra electron gets accumulated there, and the moment you provide some energy, that electron will rush from that point to the conduction. So that extra energy level, because of that external electron, that is your donor energy level. Okay, so this was about the types of the semiconductor. here was the properties of the semiconductors. Thank you.